sorry for the delay of my defense. And thank all of you here for coming my master defense. And the title of my defense and my master project is extracting the integrated Stuck's waffle effect from the cross correlation of wise galaxies with Planck CMB temperature sky maps. My name is Dani and my Chinese name is Zhao Junyi. And in the past 2 years, I'm under the supervision of Professor Tomosu Goto, so my biggest acknowledgement belong to him. And okay, here is the outline of my defense. First, I will talk about the background and motivation of my master project, and then I will outline the theory applied in my master project. And then I will go through the literature a little bit, and then I will talk about the data sets used in my master project, and then I will show you the analysis and results. And in the end, I will close my defense with the summary. And then, okay, here is the background of my master project, dark energy. Dark energy is one of the biggest puzzles in modern astronomy or in modern physics. And then first, Reese in 1998 and promoted in 1999 find the expansion of the universe is accelerated. Okay, they measure the distance of universe through type 1a supernova, and then they find that from the distance they measure, they find that the expansion of the universe is accelerated. And then if Einstein is correct, then the driving force for this accelerated expansion is dark energy. And in their papers, in these two papers, they find that the cosmological model fit the data points the best with dark energy. So, and then in addition to type 1a supernova, there are many other probes which can detect dark energy. For example, this plot. Here is the latest Planck data combined with BAO and with lensing, and then they detect 68.3% of our universe is dark energy. And although the exact amount of dark energy among different probes vary, they roughly agree with that around 70% of our universe is dark energy. However, we still cannot answer what is dark energy. We still don't know what dark energy is. So we should try every possible way which can help us to understand dark energy more. And then there is an alternative method, the integrated waffle effect, the ISW effect. And this effect is related to the imprints of dark energy in gravitational wave. And now I'm going to explain it. So, okay. First, the theory of ISW effect is first proposed in 1967, followed by a detailed study in 1968, and then it says that when a photon coming out from cosmic microwave background, while it crossing through a gravitational wave, first it will get the blue shift while it falling in the gravitational wave, and then it will get red shift while it climbing up from the gravitational wave. So if the universe is dominated by matter, not dark energy, then the gravitational wave is frozen do not decay with time. So the redshift and the blue shift on the CMB photon cancel each other. So there is nothing changed on the CMB photon. But if the universe is dominated by dark energy, then the gravitational well will decay because the accelerated expansion caused by dark energy. So while the CMB photon crossing through the gravitational well, the well decay. Then the redshift on this CMB photon no longer cancel the blue shift on the CMB photon. So you will see totally the CMB photon get net blue shift, so it becomes hotter. Mathematically, you can see from this simple formula, this is the gravitational well and the derivative of the gravitational well. So if this derivative with time is not zero, then there will be a temperature fluctuation on CMB. I'm going to show you an animation which helps us to understand ISW effect more. First, you see the gravitational well decay, and the color change here. The color change here corresponded to the temperature change on the CMB photon because of ISW effect. While the photon coming out from the gravitational well, the photon become hotter. Then, however, this effect is too small. We cannot see it directly through the CMB alone. But fortunately, in 1996, from this paper, they proposed a way to detect ISW effect, which is through the cross correlation between CMB and large-scale structure. And more fortunately, in 2000, there is a paper which detected the ISW effect exactly through this method. So now I'm going through the literature review a little bit. So, since I just mentioned that to detect ISW effect, one convenient way is to measure the cross correlation. So among those cross correlation studies, many people use data from DARTmap for the CMB, and then only Plum collaboration themselves use Plum data to study ISW, and then for the galaxies used in the cross correlation, and there are many kinds of galaxies available. SDSs, NVSs, 2-mass-wise, and then among the literature, most significant detection is of ISW effect is around 2 to 3 sigma, which is not so significant. Okay, and here I would like to talk about the data used in the cross correlation studies. And first, here I list some important properties of the data which has been used in previous ISW studies. For CMB, COB, DARTmap.plum, galaxies, SDS, 2-mass-wise. And first, let's look at the CMB side. Okay, we know that the average temperature of the CMB skies is around 2.73 Kelvin, and the temperature fluctuation is micron Kelvin. So comparing these to each other, the temperature fluctuation is 1 in a million, which is really small. And actually, not all the temperature fluctuation is caused by ISW effect. As you can see in this figure, compared to the total temperature fluctuation, the fluctuation caused by isostatic effect is still small. So hence, because this effect is small, so we need a good sensitivity for the CMB data. So, and the literature tells us that the sensitivity should at least as good as WMAP. Because in this table you can see that nobody has detected isostatic effect through COBE, but they do have detected the isostatic signal through WMAP. So at this you need this sensitivity. Of course, the Planck is even better than WMAP. Then, so in my master project, I use Planck as the CMB source. Then let's look at the other side, galaxies. So galaxies work as the tracer of large scale structure, and just first it should be wide enough, because if you only detect the ISW signal in a small area of sky, it is really hard to convince people that you do detect the ISW effect. So first you should conquer the cosmic variance. So the survey area of galaxy side should be as wide as possible. So among the three main galaxies which has been used in previous studies, two main wides are the best because they are all sky. DSS only have a quarter of the skies. Then, but is wide. Is all sky good enough? So from literature we know that we should have large number of galaxies for the correlation studies, and this it's better to have 10 to 7 galaxies. This is the most ideal case. So now an ideal survey for ISW is not only wide but also deep. So among these two, all sky survey, TMS and WISE is much deeper than TMS, as you can see number here. So in my master project, I use WISE as a source of galaxy. Then we have to select galaxies from WISE. We know that ISW signal is sensitive to the galaxy counts, so we need a uniform galaxy sample. So how do we select a uniform galaxy sample from WISE? First, WISE is a mid-infrared survey, and it has 4 bands: W1, W2, W3, W4. And first we know that galaxies' colors are redder than stars. Okay. For example, let's look at this color diagram. The red object in this diagram are the object from this area between galactic latitude 59 degrees and 60 degrees. And we know that the object in this area are mainly galaxies. And then the blue object in this color diagram object in this area between galactic latitude 5 degrees and 5.1 degrees. We know that the object here in this area are mainly stars. So you can see the difference of color among galaxies and stars. So we can select galaxies by color codes. Then, for example, if we apply these color codes, we can use the object here. Then the object we select are mainly galaxies. You know this from color diagram. So here comes the question: which cards can select the most uniform galaxy sample? sample, if you only decide the cuts by eyes, then it thinks that, okay, maybe this cut gives you the most uniform galaxy sample, or this cut, or maybe this cut. So, and actually, previous ISM study select galaxies depend on color cuts, but they decide the color cuts by eyes, which is not quantitative ways. Hence, in my master project, we develop a method to quantitatively evaluate the uniformness of the object we select, and then based on that uniformness, we select the most uniform galaxy sample for the cross correlation. Then I'm going to explain a little bit about my method. Okay, this method is based on the magnetic cut of W1 and based on the two color cuts on W1, W2, and W2, W3. Then first, every time we apply cuts, we map the object here in helipix format map. So this is a pixel format. Then we investigate the object density in pixel based on the galactic latitude coordinate here. And then I define the number to describe the uniformness of here. So the number mu I define is that the smallest the mu is the uniformness the galaxy sample are. So I try to find the smallest mu. So okay, I apply other cards and then I map this map in helipix format and I calculate mu. Then okay, I apply different cards and then we get the different helipix map and then we get different mu. Then okay, I change these three constraints independently from each other, and so I calculate every possibility, and I calculate the correspondent mu for every possibility, and then we find that if we apply the negative cut W1 lower than 15.3 and apply the color cuts W1, W2 larger than 0, W2, W3 larger than 2.4, then we get the most uniform galaxy sample. And for you to easily understand these three panels are the 2D projection of this 3D pyramid space. So you can see that in the contour, mu is the uniformness of the galaxy sample, and the smaller the best, the smaller the better. So you can see here, this is the smallest, this is the smallest, this is the smallest. So here, 2.4, 2.3, 0. And then I can show you two examples of selected galaxy sample, and this is a bad example. This is a good example. In bad example, you can see that the helipix map is quite colorful, which means that the distribution of the galaxy is not so uniform. And in good example, you can see that the helipix map is quite, what's it, in a single color, purely blue. So it means that the distribution of galaxy is uniform. Then, so with the galaxy sample we selected by the method I developed in my master project, I applied this two foreground mask to study the different foreground treatment affect the, I would like to know whether the different photon treatment affect the ISW signal. So I will apply two masks. This U73 mask is from Planck, and this K275Y9 is from Dani. Okay, as you can see, two masks sample a little bit different. So here I'm going to show you the analysis and result. We did a careful analysis. We measure the cross correlation of our galaxy sample and 4 different Planck CMB maps. And we also investigate the cross correlation under different galactic latitude cuts. And of course, I apply the 2 different photon masks. One is U73, and the other one is K275Y9. This is from Dani map. Let's take a look of the result. Okay, I take out one of the panels to show you the result. First, if there is no ISW signal, then it looks like here. 0 and blackish. Then, okay, this green dash is the lambda CDM prediction of our galaxy sample. Then, okay, here, the black dots are the cross power spectra of our galaxy sample with Planck CMB maps. So this is the original power spectra.
What is the x-axis here?
X-axis?
Yes.
Okay. It's the scale of the temperature fluctuation. It's the scale of the cross correlation. So here, L's, if smaller the L, the scale, the larger the scale. So here, the larger the L, the smaller the scale. And ISW is a large scale temperature fluctuation, so we only need the smaller L. Then here, the red line is the best fit of this resulting cross power spectra. This is the fit red line. Then, okay, because some previous study also being the power spectra, so we follow 2 previous studies being the power spectra, and this is error bar. Then we also check the best fit model for beam powers. They are quite consistent with each other in this case. Then, okay, do we get the ISW signal? Yes. Okay, around 1.2 to 2.5 sigma is here. And we get a signal, but is the result consistent with lambda CDM prediction, or our result is larger than lambda CDM prediction? So, okay. The amplitude for best fit here, if this number equal to 1, it means lambda CDM prediction. So actually our result is consistent with lambda CDM prediction within 1 sigma. Then, okay, we also perform more careful statistical analysis. Okay, the delta chi-square means larger than 3 means strong evidence of ISW effect. So I'm going to explain a little bit of delta chi-square. So delta chi-square is chi-square of 0 means no ISW effect. Subtract the chi-square from best fit. Okay, you can see that the blue arrows here represent a totally illustration of the chi-square for best fit. The data points. zero ISW signal from this black dash to those black points. So of course, that fit model has the smallest chi-square. So we take a look of the chi-square for zero ISW signal. So if this number chi-square for zero is large, then it means that the data points are more powerful to reject the null hypothesis. The null hypothesis here is no ISW effect. So if this number is large, then the delta chi-square is large. So large delta chi-square values means that our data are more powerful to reject the null hypothesis, which means there is no ISW signal. Then, so let's take a look at the delta chi-square value of my result. So here we do have some delta chi-square values larger than 3. So we do have the strong evidence for ISW effect. Then, okay, I'm going to close my defense with summary. Okay, in my master project, I use the best data set which is available so far, WISE and Plonk. Let's recall this table again. Plonk is the most sensitive CMB data we can use now, and WISE is the deepest all-sky survey so far. So I do use the best data set in my master project. Then we perform a careful analysis. Okay, first we optimize the galaxy sample quantitatively. Okay, let's recall this contour, this 3. So I do develop a quantitative method to select the most uniform galaxy sample. Then I also did a careful analysis. I do measure the cross correlation. I do investigate these 4 different CMB maps, and I apply 2 different maps to study the difference. And I also investigate 3 different galactic latitude cuts. So, and then my results are consistent with standard CDN expectation, and we detect dark energy at 1.5 to 2.2 sigma. And this, because we use ISW effect to detect dark energy, and this is an independent method from other probe, such as hyperbolic supernova and BAO, because every probe has their own problem, so it is important to use an alternative independent probe to detect dark energy, which can help us to understand dark energy more. So, thanks for listening.
Okay. Do people here have questions?
So for your cross correlation part, can you have the uncertainty from observation?
Oh, yes. The uncertainty will come from the number of galaxies we select. So if the main uncertainty we have from observation will be the number of galaxies we select. So if the number of galaxies we select is small, then the uncertainty will become higher. I can show you the other indicators. Okay, so if because for a galaxy sample, we need to know the galaxy bias of our galaxy sample to further study the ISW effect. Then we measure the autocorrelation. to get the galaxy bias of our galaxy sample, then this line, this gray line, can you see that? Is the uncertainty of the bias. So I think you see when you say the uncertainty, then the main uncertainty will be here. And also the other uncertainty from CMB is that okay, so like when we when we try to get the best fit result, we use the covariance matrix, and this is related to the CMB, mainly related to the CMB errors. So, but we only have one CMB sky to study, so we simulated 1,000 CMB map, and then measure the cross correlation for 1,000 times to get the error. And then the error will be in the covariance matrix, and then from that covariance matrix we get a best fit result. So that's how that's how the error comes from.
Yeah, so for your plot of error and cross correlation, the data point is still very scattered. So
Yes.
if considering the uncertainty from observation, will it be better to say your getting is good?
You're saying that this.
Yes.
Okay, but you can see the fit. Okay, like this data points we have like 80 points, so we have 80 degree of freedom. Then you can see from here the reduced chi-square is nearly 1. If you are going to try to, if you want to know whether it is a good fitting or not, then I think it's good enough.
I think you can fit it with a straight line and still get it.
Okay, I see. But first, you practically, if you are going to fit data, you need a formula, right? So in most ISF study, we fit from the lambda CD prediction. So we usually fit the multiple of the theoretical predictions.
But I think what I can believe is that the data are not consistent with each other.
Right.
But whether it's consistent with lambda CDM or consistent with a straight line, I just draw with my hand. It's
Okay.
hard to say.
So that's why some study use gain powers because it can ignore some the correlation or some noise here. So that's why many literature use gain powers. And but let me show you the best fit for gain powers is quite consistent. It's the one without bailing.
I think the most important conclusion of you is it's not consistent with zero.
Zero.
So
Right.
you convince well, so that's good.
Okay.
Supin, do you have questions?
That's I spend.
It's still connected, right?
Hello?
Yes.
Okay. On this diagram, your first point seems to be a bit strange. So I think being data, when you being the data, you do a kind of average. So it's kind of strange to me. The first point,
This one?
your big data jump up a lot.
Yes. Because first, the bin size there is small. So the error are also large too. And then in this scale, CMB might have some problem in resolution.
Can you say it again?
Okay. Okay. First, the first thing here, you say it is strange for you that it is large, right?
Right.
And then, okay, the bin size for the first bin is only 2. I mean, only L equal to 6 and L equal to 7. And then, so of course you see the error bar also large. Then the other point is that CMB has some resolution problem while it told the whole sky. Yeah, so lower the L, the bigger the problem is in CMB resolution.
Okay.
Isn't there a point above the floating range?
I believe some.
So that is that one?
Uh,
There may be a point about like 1.3 or 1.4 or something like there. So if you take average.
yes. I take the median. So if the bin size only 2 here, then it's the mean of that 2, right?
So you say you do have a point at the 1 point something?
Yes.
Okay, then that's good. But I think it should be short somewhere. Yeah. Okay. Another thing is I'm not quite clear how the say you said you want full coverage of galaxy on sky. So you select this all sky data set.
Yes.
But maybe because your signal to noise is so low, so maybe this SDSS is not bad because it at least covers 1/4 of the sky, and maybe it has much better signal to noise ratio. That give you more scarcity sample. So I don't know how to judge the sky coverage and the sensitivity. So do you?
Yeah, I agree that. I agree that. But I mean, the main point here is WISE is the best data we can use so far. So yeah, and SDS is yeah, sorry, here. So
Your image is freeze. I don't know why.
yes. Right, but if you only have 1/4 of the sky, the cosmic variance is also large, right? So
Can you point out in the equation what would that affect you? Because I guess you would only lost a couple points in the large L. No, I'm sorry, small L. So small L. Right? So more than 1/4 of sky, all the L you can recover.
okay. To my understanding is that if you want to measure the cross correlation, then if the sky is small, then the cross correlation will also become unstable. So it will be more scattered in the data point too. So I agree that SPSS is not that bad for ISW study because there are many literature use SPSS too, but we just try to use the best data like OSCI and deep enough to study ISW. Yeah.
Okay, but now question for you. You mentioned that in the literature review that you can prove other studies show 2 to 3 sigma.
Yes.
But now you only show 1 to 2.2, right?
Yes.
So one is better than 2.
Okay. Well, I can say that comparing to literature, that we perform more careful studies. Like they didn't study the.
So you think although they get 2 to 3, they may not do things as carefully as you did, right?
They are okay. First, they select the galaxy sample, not in quantitative ways. So, from this point, we perform our analysis is more careful, and the other is that for the literature using WMAP, they don't have this. They cannot perform this detailed studies. But we use Plum first. We have higher sensitivity, and Plum itself didn't do very careful analysis of these 4 different foreground claim maps, but we did. And then they didn't study the influence on ISW signal from these 2 different foreground treatment, and the other is that they didn't perform a careful study here. So our result comes out after the careful analysis, but.
Well, you cannot make excuse out of people are not careful, right?
Yeah, I didn't say they are not careful. I just say our analysis is more careful, right?
I thought that you were saying you have 4 different foreground. That's careful part. Is that right?
Yes.
Because you could have different masks.
Yes.
Maybe I don't know. Maybe you can have a table that in a paper. Okay, so I'm done.
Thank you.
Just to add a little bit, like for example, in my previous paper, I detected this with 3 sigma, but I was using half the data Dani is using now.
Okay,
so you can tell which one is more trustworthy.
Okay, but now your sigma is lower. But I get your point. This is non-zero, and it's significantly up non-zero.
Yes.
Okay, I have a question. You talk about the uniformness of the sample.
Yes.
What is, suppose you have a sample that's not uniform. For example, in your W1 minus W2.
Yes. If we apply different colors.
Right. If you apply a different color cut and get a non-uniform sample, what's the source of the non-uniformity?
Mainly from stars.
Okay.
Yeah, the foreground stars. Because in large scale, the universe is uniform.
So you are saying your W1, W2 selection is basically to remove stars?
Basically okay, yes, one of the goal is to remove stars, of course, on cards, right? And then the other goal is to get the most uniform galaxy sample. Because some object you
Because galaxy should be uniform.
Yeah.
There's no spatial direction in the universe.
I mean, but the distribution of the galaxy on the whole sky should be uniform. But I agree that some color cards may give you more number of galaxies, but the distribution may not be uniform. And then for cross correlation study, we need
I see. So if the main goal is to remove stars, maybe you can combine two mass and WISE using K, W1, W2. In this color space, you should be able to remove most of the stars.
You mean combine the two mass?
So here, so can I have a comment? So, but yeah, we discussed this a little bit combining two mass, right?
Yes.
But
the sample will become even smaller.
yeah, so if we combine two mass, like we didn't want to be limited to the two mass detected objects, then it will be shallower and reduce the number of galaxies. So that's the main reason we chose not to combine two mass. Of course, there could have been options to partially combine two mass, but then
Yeah, or if just use WISE in the W1, W2, W3 color space.
Oh, okay. I mean, not use the magnetic space.
No, because in principle galaxies should be uniform. So if in the color space you can clearly separate stars in the galaxies.
maybe you can show up the color magnitude plot.
Oh, I didn't have magnetic color here.
Okay, but before that you have a plot. You show the different colors. Okay, so this is the color file. Blue are the mainly stars, right?
Yes.
So where was your color file?
0 and 2.4. Yeah. Because around this area, it's hard to decide the colors on my eyes. And
So most of the red objects are in your color chart, but some blue are scattered into your color chart.
yeah. So that's why we need a quantitative method to see how uniform it is. Because if you only move a little bit here, then it's hard to say which parts is better. Yeah. And if you are saying the magnitude, I think it is related to the wide survey. Because originally their depth is different area of the sky. So we survey this to get
I have a second question.
yes.
You mentioned the theoretical expectation from the CDM for your galaxy sample.
Yes.
How did you calculate? Could you tell us?
Yes.
To do that, you need to know what kind of galaxy sample it is.
Yes. So here, first we have to know the redshift distribution of our galaxy sample. So, but WISE is not a spectroscopic survey, so we cross-match WISE with gamma, which is a spectroscopic survey, and then this is the redshift distribution, and the red one is the cross-match sample, the blue one is gamma, and the median redshift of this cross-match sample is here. So the median, so you can say the redshift of our sample is 0.158.
There must be many gamma galaxies without redshift. No, many WISE galaxies without gamma redshift.
Yeah, because maybe, yeah, there are around 1/3 of our sample. Do not have redshift. We do not have counterparts in gamma. And one reason is that those galaxies are more deeper, more far from us. So
High redshift.
high redshift.
Yeah, suppose those 1/3 of galaxies have a redshift 0.5.
Yes. Okay. I can tell you that because I also cross-match our sample with SDSS, and I also cross-match our galaxy sample with Z Cosmos, and then I do get the higher median redshift, but when I put that redshift, put different redshift to calculate the theoretical prediction, the theoretical prediction is nearly no change. It's nearly 0.1% or 0.1%. Then also for the theoretical prediction, we also need to know the galaxy bias, which I just talked before. Then I use this to get a theoretical prediction.
Any more questions from people here or from Sutin?
No.
So, how do you want to leave? Now, should we ask people to leave?
Yes, I think we have a little close discussion on that.
With him? With her?
Without her.
Without her?
It depends on company. I heard just they it depends on chair.